Hello, welcome to the course on pericyclic reactions and organic photochemistry. We are on the third week of this course and we'll start with module number 11 on the pericyclic reaction. We have a few more topics to cover under the Diels Alder reaction, namely the intramolecular Diels Alder reaction. Diels Alder reaction is involving heterodienes and dienophiles, Lewis acid mediated or Lewis acid catalyzed Diels Alder reaction, and finally asymmetric Diels Alder reaction, which is a very important topic in the case of Diels Alder reaction. Now intramolecular Diels Alder reactions are those reactions where the 4+2 cycloaddition takes place within the same molecule. If you look at this particular structure here, the diene and the dienophile are built in within the same molecule, and hence the reaction takes place within the single molecule, which is known as the intramolecular Diels Alder reaction. There are many examples of intramolecular Diels Alder reactions known. Let us consider a few examples in this particular module. If you take this particular molecule, in this molecule the pendant group is attached in the form of a dienophile from the one position of the diene, in so much so that the stereochemistry of this particular double bond is E in this particular case, and the stereochemistry of the dienophile is also E in this particular case. So when this reaction is carried out at 150 degrees, these two adducts are formed, and you can tell from the stereochemistry of this particular ring junction where this hydrogen here on the one position of the diene and the two position of the dienophile are trans with respect to each other. It is possible only when there is an endo kind of an approach. So this adduct is arising out of the endo approach, and this particular adduct is arising out of the exo approach in the ratio of 60:40 ratio. The exo-endo adducts are formed as a mixture in this particular case. Now here is a substituent which is attached to one position, but the stereochemistry is reversed. Here it is a E stereochemistry, now it is Z stereochemistry in this particular case. In the case of the Z stereochemistry, if you look at based on the stereochemistry of these two hydrogens, you get exclusively only the endo adduct in this particular case. So depending upon the stereochemistry of the attachment of the pendant group, which is the dienophile group in this case, otherwise the pendant group, the lengthwise number of carbons and the kind of dienophile, they are essentially same except for the stereochemistry of attachment at this position 1 in this particular diene here. So depending upon the stereochemistry of the carbon-carbon double bond of the diene in this particular case, the exo-endo ratio varies quite dramatically. In this case you get exclusively the endo adduct compared to the case where here you get a mixture of exo as well as the endo adduct in this case. Here is another example of an intramolecular Diels Alder reaction, except the pendant group is now attached to the two position of the diene, not at the one position like the earlier example. When the pendant group is attached to the two position of the diene with this much length of the dienophile, there is only one possibility of orientation of this dienophile. The dienophile essentially orients in this particular fashion as it is shown, and the reaction proceeds to give the adduct which is the bridged bicyclic adduct. In the case of these two systems, you get the fused bicyclic adduct, whereas in the case of the two substituted butadiene, you get a bridged bicyclic system as one would expect in this particular case. Now it is possible to attach the diene and dienophile through as a temporary connector like the silicon connector in this particular case. The diene is an alcohol, the dienophile is also an alcohol. The alcoholate is reacted with the diphenyl silyl dichloride to get this silicon bridged system. In other words, this is a tethering that is used, which is removable tethering in this particular case. So heating this particular diene-dienophile combination essentially results in the formation of the adduct which is shown here. This adduct is essentially the endo adduct of this particular molecule. From this, the silicon can be cleaved off by acid catalyzed hydrolysis of this particular lactol kind of a derivative that you have here. So the hydrolysis essentially leads to the formation of the dialcohol. Under the conditions of acidic condition, the esterification takes place in this particular case. So the esterified product, which is the lactone product, is what is obtained during the course of the intramolecular Diels Alder reaction, followed by the workup, which is the acidic ethanol methanol workup. Acidic methanol workup is essentially an alcoholysis of this particular silicon derivative and that essentially results in the formation of the alcohol here, which undergoes the lactonization process to give this particular lactone that is shown here. Here is an interesting example. The alcohol is first treated with butyl lithium to get the corresponding lithium salt, and then it is treated with vinyl magnesium bromide. The intention here is to exchange the lithium with the magnesium such that the magnesium vinyl bromide gets attached to the alcoholate, forming the magnesium alcoholate, such that it brings the diene and the dienophile close together. When it is heated to 80 degrees and then quenched with water, essentially the magnesium salt is hydrolyzed when it quenched with water. Heating to 80 degrees results in the formation of the Diels Alder reduct, which is shown here, and the stereochemistry of these two ring junctions that are this particular junction, this particular carbon and this carbon essentially cis with respect to each other, as one would expect in the Diels Alder reaction. So this is an example where the vinyl magnesium bromide is essentially chelated to the oxygen of the alcoholate, resulting in the formation of a Diels Alder reaction, which is an intramolecular Diels Alder reaction of a magnesium tethered compound. These are examples of intramolecular Diels Alder reaction where the pendant group attached is a vinyl group in this particular case, and the diene is essentially a very reactive diene, which is a enol trimethylsilyl ether kind of a diene. When it is heated at 250 degrees, for example, there are two possible orientations this dienophile can take with respect to the diene, and in one case, one orientation, as it is shown, for example, gives you the Diels Alder reduct, which is this particular Diels Alder reduct. If you orient it the other way around, in other words, if you bring this carbon over here and this carbon over here, that would give the other orientation, which results in the formation of this particular Diels Alder reduct. On the other hand, when the dienophile is biased by an electron withdrawing group, then only the para kind of a substitution pattern is obtained. If you look at the orientation of this diene and the dienophile, this is an endo orientation, and also it is an orientation where the OTMS group and the COOME group are para with respect to each other. You can see here the para relationship. So the para-like product is what is initially formed. The TMS silyl group is hydrolyzed by methanol in both cases. The top equation as well as the bottom equation, the workup is done by methanol, essentially to cleave off the O-trimethylsilyl group to get the ketone back. The enol will essentially undergo keto-enol tautomerism to give the ketone, which is the cyclic adduct which is eventually formed during the course of this reaction. These are some interesting examples of the diene being generated in situ during the course of the heating. In this particular case, this sulfolane, the benzosulfolane, is heated. Sulfur dioxide is eliminated. It is a chelotropic reaction. You will see some examples of chelotropic reaction at a later stage. For the time being, assume that the sulfur dioxide elimination results in the formation of the orthoquinodimethyde in this particular case. This vinyl group is a built-in vinyl group. So this tether essentially brings the vinyl group in close proximity to the diene, and as a result of that, the Diels Alder reaction takes place to give an estrone as the product in this particular case. This benzcyclobutane derivative is heated in orthoxylene, reflexing orthoxylene for example, to produce this orthoquinodimethyde as the intermediate. The orthoquinodimethyde has a acetylene group which is a built-in acetylene group, and that pendant group brings the acetylene group in close proximity to the diene, resulting in the formation of a 4+2 cycloaddition reaction to give this particular reduct, which is the Diels Alder reduct in this case. Here the diene is actually an alpha pyrrone derivative. The alpha pyrrone derivative can undergo Diels Alder reaction with this particular vinyl derivative, which is attached to through a pendant group, which is this particular pendant group in the form of an amide linkage. Diels Alder reaction in reflexing xylene produces this particular adduct. This adduct is not stable under the reaction condition. It undergoes the loss of CO2. By means of loss of CO2, you generate this diene fragment in this particular system. This kind of CO2 bridged systems are angle strained because one cannot maintain 120 degree angle of the carbonyl sp2 carbon in this particular case. So such an angle strain is released by means of elimination of carbon dioxide in this case, and as a result of that carbon dioxide elimination, this adduct is formed, which is the Diels Alder adduct of the pyrrone with respect to the Diels Alder reaction with the vinyl derivative, that is the pendant group here. Let us move on to the hetero Diels Alder reaction using a heterodiene or a heterodienophile. In this particular case, we are dealing with the iminium ion as a dienophile, and intermolecular examples are shown here. The iminium ion is produced in situ by a reaction of a primary amine hydrochloride with formaldehyde with the loss of water, for example, resulting in the formation of an iminium ion. If the synthesis of the iminium ion is carried out in the presence of a diene, which is in this particular case 2,3-dimethyl-butadiene, then the 4+2 cycloaddition reaction essentially gives you a tetrahydropyridine derivative in this particular case. You can see here this is a 4-pi component and a 2-pi component, which is the iminium ion, which is an electron deficient in nature, and that is why the reaction essentially proceeds at room temperature or so, giving this particular derivative, which is the tetrahydropyridine derivative. Here is an iminium ion which is generated from the aldehyde and the primary amine, and that reacts with the cyclopentadiene to give two types of adduct, the exo-adduct and the endo-adduct. This is exo with respect to the carbonyl functional group and the bridge here, and this adduct is an endo-adduct with respect to the carbonyl functional group and the bridge that is given here, for example. Now, the carbon-nitrogen bond in this kind of an adduct can be easily reductively cleaved to give the primary amino derivative of this kind, and that has been exploited in the synthesis of the amino alkyl substituted cyclopentene derivative with the stereoselective formation of the cis isomer of the 1,3-disubstituted cyclopentene derivative from the reductive cleavage of the carbon-nitrogen bond from this kind of an adduct. Here are some interesting examples of intramolecular versions of the iminium ion Diels Alder reaction. This particular aldehyde, which has a built-in diene, is reacted with benzylamine hydrochloride. Upon reacting with benzylamine hydrochloride, it forms the corresponding iminium ion. The iminium ion undergoes the Diels Alder reaction, which is an intramolecular Diels Alder reaction. Here, both the exo as well as the endo adducts are formed in 2.5:1 ratio, for example. So the corresponding Diels Alder adduct is what is formed. There is a double bond missing in this particular structure, so please correct it that this would essentially result in the formation of a adduct with a double bond in this position and a double bond in this position in this case. Now, the iminium ion is formed in situ by reacting this primary amine. Here aldehyde is taken and reacted with the primary amine. Aldehyde is part of the diene. Now the amine can be part of the diene, and it can be made to undergo reaction with formaldehyde to produce the corresponding imine in this particular case. So the primary amine and the formaldehyde react together to form the imine, and the imine undergoes the Diels Alder reaction, which is a hetero Diels Alder reaction, to produce the corresponding bicyclic derivative, which is this bicyclic derivative. The orientation of the imine and this diene can be exo or endo. That would result in the relative stereochemistry to be either cis or trans, as the case may be in these two cases. Now, in this example, this carbamate is heated initially. The carbamate undergoes the loss of ethyl carbamate in this particular case, resulting in the formation of an imine, which is a ethyl carboxylate substituted imine, and this is essentially a imine carbamide kind of a derivative is what is generated, and that reacts with 1-phenyl substituted butadiene to produce the corresponding phenyl substituted tetrahydropyridine derivative in this particular case. On the other hand, it reacts with this particular diene to produce the bicyclic system, which is this particular bicyclic system, which is a Diels Alder adduct arising from this intermolecular Diels Alder reaction between the diene and the dienophile, producing this kind of Diels Alder adduct in this case. Now, these are interesting examples of synthesis of gamma pyrrone derivatives from the so-called diene, that is this particular diene. This diene is known as Danishevsky diene. Danishevsky diene does not have these two methyl groups, so it is actually a dimethyl derivative of the Danishevsky diene. You can see here this diene is endowed with electron-rich functional group, namely the methoxy and the trimethyl silyl oxy derivative. It reacts with the aldehyde, which is benzaldehyde in this particular case, in a Diels Alder fashion, to initially give a regioselective adduct, which is this particular adduct. You can see here this is an orthopara kind of a product is what is ortho with respect to the methoxy and para with respect to the thionyl oxy derivative, and this particular adduct is exclusively formed during the course of the hetero Diels Alder reaction. It's a hetero Diels Alder reaction because the dienophile is a carbon oxygen double bond and not a carbon carbon double bond in the early, as in the case of earlier examples. So this is a heteroatom substituted dienophile. The hetero Diels Alder reaction essentially produces this oxygen heterocycle. This oxygen heterocycle can be made to further undergo desilylation reaction with the loss of methanol, for example, in the presence of boron trifluoride TFA mixture or zinc chloride TFA mixture, to essentially produce these two adducts which are arising out of this particular stereochemistry of the two orientations that are possible for the diene and the dienophile. The exo-endo orientation essentially determines the stereochemistry of these two junctions, that are two carbons that are produced during the course of this particular reaction. This is another example of a Daniszewski diene reacting with an imine. The earlier case it was a reaction with an aldehyde. In this particular case it is a reaction with an imine, and the Daniszewski diene is this particular diene, which is a 1-methoxy 3-trimethylsilyl butadiene in this particular case. The initial Diels Alder adduct structure is shown here, and the mechanism of loss of methanol with the trimethylsilyl group is what is shown to yield this gamma pyridone derivative in this particular case. A nucleophile, which could be, for example, methanol or chloride or fluoride ion, for example, reacts with the silicon center with the loss of the carbon silicon bond cleavage with the simultaneous loss of the methoxy group in the third position of the molecule, resulting in the formation of the gamma pyridone derivative, which is shown as the final product during the course of this particular reaction. Here is an example of a hetero Diels Alder reaction where the diene is having the heteroatom and not the dienophile. Until now we had imine and aldehyde as the hetero dienophiles. Now we are dealing with the Diels Alder reaction where the diene possesses a heteroatom, in this particular case nitrogen. If you look at this derivative, this is nothing but an alpha methyl acrolein, which is the aldehyde, forming a hydrazone with N-dimethyl hydrazine, for example. So if you react alpha methyl acrolein with N-dimethyl hydrazine, this is the hydrazone that one would produce, and that hydrazone is acting as the heterodiene, reacting with the maleic anhydride as the dienophile. The reaction is essentially taking place at room temperature, resulting in the formation of the Diels Alder adduct. The Diels Alder adduct is now undergoing a hydrolysis with methanol to produce the corresponding carboxylic acid. The anhydride is hydrolyzed to carboxylic acid. Then it is treated with the diazomethane to produce the corresponding ester. So this is a part of a natural product synthesis, for example. The piperidine derivative that is produced is highly stereoselectively produced in this manner. The final reaction is essentially a nitrogen-nitrogen reductive bond cleavage by treating this hydrazine derivative with zinc and acetic acid, where the reductive cleavage of the nitrogen-nitrogen bond results in the formation of the piperidine derivative that is shown here. The stereochemistry of the two carboxylic acid groups are cis with respect to each other, essentially because it is coming from initially an anhydride system which is cis with respect to each other. So that cis stereochemistry is retained during the course of the reaction. This relative stereochemistry between this carbon center and this carbon center would essentially depend upon whether it is an exoadduct or endoadduct. That is not properly defined in this particular case because it could be a mixture of exo or endoadduct that is formed. This stereocenter is essentially produced by a reduction of the carbon-carbon double bond. So that can be, both the enantiomers can be produced under the conditions of zinc acetic acid reduction of the carbon-carbon double bond in this particular case. The enamine is reduced to the corresponding imine if you look at the reaction carefully. This is essentially an enamine kind of a system. It's not only a nitrogen-nitrogen bond reductive cleavage takes place, the carbon-carbon bond is also reduced during the course of the zinc acetic acid reduction in this reaction. Now here is a generation of diene in situ from this derivative. This derivative can undergo a 1,4 elimination reaction. The mechanism of the 1,4 elimination reaction is shown in this particular case. The trimethylsilyl amine and the ammonium group are the leaving groups in this particular case. When this molecule is treated with cesium fluoride, the fluoride ion essentially being highly silicon affinity nature of the fluoride ion results in the formation of the attack of the silicon by the fluoride ion, resulting in the formation cleavage of the nitrogen silicon bond, leading to the elimination of the trimethylamine as the leaving group in this particular case, results in the formation of this particular diene, which is a heterodiene. A built-in dienophile, which is this vinyl group, essentially traps the diene that is being produced in this particular case, resulting in the formation of a Diels Alder reduct, which is this particular Diels Alder reduct that is shown in the final structure of the product that is shown in this scheme. Acrolein itself can undergo Diels Alder reaction, where one molecule of acrolein reacts as a diene, another molecule of acrolein reacts as a dienophile, resulting in the formation of a pyran derivative with an aldehyde substituent. This reaction is not synthetically very useful because it also produces polymer. As you can imagine, acrolein is a polymerizable material. Under thermal condition, it can undergo polymerization reaction to produce the polymer also. Nevertheless, acrolein derivatives can be successfully made use of in the Diels Alder reaction. Here is an example of a acrolein derivative which is undergoing a Diels Alder reaction with a ketene silyl acetal, alpha chloroketene silyl acetal, resulting in the formation of an initial Diels Alder reduct, which is this Diels Alder reduct. From this Diels Alder reduct, loss of hydrochloric acid, loss of HCl essentially produces the double bond, and the hydrolysis of this particular orthoester results in the formation of the lactone, which is shown here. So subsequently, after the Diels Alder reaction is produced, it is treated with a base to eliminate the HCl, followed by aqueous treatment to hydrolyze the orthoester to corresponding lactone, which is the alpha pyrone derivative that is produced during the course of the final hydrolysis step. This reaction is an interesting reaction for the simple reason that this is a transannular reaction. If you look at the ring, which is this particular ring, this is a medium-sized ring. Medium-sized rings, as you know, they undergo transannular reaction. This diene and the dienophile are close proximities. They undergo, this is essentially a indole derivative. It's a cyclophenic indole derivative, and it undergoes the Diels Alder reaction with the diene, which is an intramolecular version of the Diels Alder reaction. Diels Alder reaction followed by loss of nitrogen as a gaseous nitrogen is the overall reaction. The initial Diels Alder reaction is shown here, for example. You can see here this stereochemistry is cis because it is a cis stereochemistry to start with, and that results in the formation of this particular reduct. This is a structure of, or this is a structural scaffold of strychnine, which is a naturally available alkaloid molecule. So the naturally available alkaloid strychnine scaffold is synthesized using the intramolecular Diels Alder reaction between this diene and this dienophile. The reaction is carried out at high temperature in N,N-diethylaniline, which is reflexing N,N-diethylaniline more than 150 degrees or so during the course of this reaction. These are some examples of alpha pyrone undergoing Diels Alder reaction. Alpha pyrones undergo Diels Alder reaction to give initially an adduct where the carbon dioxide bridge is being present. Carbon dioxide bridge is not a very stable bridge for the reason that you have an angle strain associated with the CO carbonyl carbon, which cannot accommodate 120 degrees in this particular case. So loss of CO2 essentially produces the adduct, which is this particular adduct. So initial Diels Alder reaction between the alpha pyrone diene, which is this particular fragment as a diene, and the dienophile, which is acetylene in this particular case, results in the formation of the adduct, which is unstable under the reaction conditions of 300 degrees. Loss of carbon dioxide essentially produces this aromatic unit here. Similarly, the Diels Alder reaction between this alpha pyrone diene and this dienophile, which is the built-in acetylene dienophile, in reflexing nitrobenzene as a solvent, it's a high boiling solvent, reflects at 250 degrees or so. Initially, the Diels Alder reduct structure is not shown here, but one can imagine a similar structure of the Diels Alder product in this particular case also. This is a product arising out of the loss of carbon dioxide is what is shown, which produces this particular aromatic ring by the loss of CO2 from the initially formed Diels Alder product. So try practicing writing the Diels Alder product in this particular case following the scheme of things that are shown for this example. A very similar structure has to be drawn with a CO2 bridged adduct, which will lose CO2 to produce this particular compound, which is the final adduct of this reaction. Let us move on to Lewis acid catalyzed Diels Alder reaction. Now, when a Lewis acid is coordinated to the lone pair of electrons on the heteroatom of the dienophile, it makes the dienophile more and more electron deficient. You can imagine that something like an aluminum chloride or zinc chloride or titanium tetrachloride or tin tetrachloride, for example, they are all Lewis acidic in nature. The association of the Lewis acid to the lone pair of electrons on the heteroatom is what is responsible for the electron deficient nature of the dienophile. Now, the energy of the HOMO and LUMO of the dienophile is decreased in comparison to the uncomplexed dienophile. That brings the HOMO-LUMO gap between the diene and the dienophile closer together. As a result of the decrease in the HOMO-LUMO gap of the diene and the dienophile, the rate is enhanced because the activation barrier is reduced. So it is a fairly simple explanation to offer why Lewis acid addition to Diels Alder reaction catalyzes the reaction. There are two conditions that one needs to meet in this reaction. The dienophile should have a lone pair of electron where the Lewis acid can be forming a complex, and as a result of that the catalysis takes place because of the decrease in the HOMO-LUMO gap between the diene and the dienophile of the Diels Alder reaction components. The commonly used Lewis acids are boron trifluoride, aluminum chloride, titanium tetrachloride, tin tetrachloride, for example, or hydrolytically stable lanthanide triflates such as scandium triflate or ytterbium triflate and so on. Lithium perchlorate is also has been used as a Lewis acid in many Diels Alder reaction. Some examples to highlight the importance of Diels Alder reaction from the point of view of both the rate of the reaction as well as the stereoselectivity of the reaction. Remember, the stereoselectivity in terms of the orthopara ratio can be changed by means of using a Lewis acidic component in the Diels Alder reaction. Here is an example of 2-methylbutadiene and acrolein undergoing a Diels Alder reaction. Normally, when this reaction is carried out, the uncatalyzed reaction has to be heated in toluene at 120 degree, and you can see here the meta and para isomers that are Diels Alder adduct formed are in about 59:41 ratio is what it is formed. When the reaction is carried out in benzene using tin tetrachloride as a Lewis acid catalyst, what is the role of tin tetrachloride? It will essentially form a complex with the lone pair of electrons on the oxygen of the dienophile in this particular case, and thereby decreasing the HOMO-LUMO energy levels of the dienophile, bringing the HOMO-LUMO energy level closer together between the diene and the dienophile. You can see here, first of all, the reaction temperature is reduced to room temperature. The reaction takes place at room temperature in the presence of Lewis acid catalyst, which means that it is really a catalyzed reaction because the activation barrier has been brought down. In addition to that, the added benefit is that the para isomer is almost exclusive product in this particular case. In the absence of a Lewis acid, for example, you have a mixture of para meta isomer, whereas in the presence of a Lewis acid only the para isomer is formed more or less exclusively in this particular case. The meta isomer is a very small amount of 4% is what is formed. The endo-exo isomer ratio can also be affected by the Lewis acid catalysis. It's a reaction between cyclopentadiene and methyl acrylate. And the uncatalyzed reaction at 0 degrees it takes place to an extent of about only 22.5% or so, the conversion. The endo-exo ratio is 82:18. The endo is still the predominant product in this particular case. However, when aluminum chloride is added to this reaction mixture, the reaction proceeds to give 84% yield at 0 degrees at certain period of reaction. And the endo-exo ratio is now more in favor of the endo adduct, which is 93:7 ratio. When the reaction is carried out even at lower temperature, the reaction essentially goes to completion to 81%. And the endo-exo ratio is further enhanced to about 97:3 ratio. So the advantage of the Lewis acid catalysis is not only rate enhancement, it also enhances the exo-endo ratio or the ortho-meta ratio kind of regioisomeric ratios are also improved during the course of the catalysis of the Diels Alder reaction. Here are two examples where scandium triflate is used as a Lewis acid. Scandium is in scandium 3 oxidation state, and it can undergo chelation between these two oxygens of the carbonyl functional group of this particular pendant group that is shown in this particular structure. The reaction is, the scandium triflate is used only to an extent of 10 mole%, so it is truly a catalytic reaction. The reaction between cyclopentadiene and this particular dienophile results almost exclusively in the formation endo product as a major product in this particular case in the ratio of 87:13 ratio. Now here is an example where the hetero Diels Alder reaction, the imine is formed in situ. This is something we have seen, except this is now catalyzed by scandium triflate and magnesium sulfate as the Lewis acid combination in acetonitrile. So the iminium ion that is produced initially can coordinate to the scandium triflate, in making the scandium triflate coordinated iminium ion to be a much more reactive dienophile, and that undergoes the Diels Alder reaction to give this pyridone derivative after the hydrolysis of the trimethylsilyl group and loss of methanol from the Diels Alder product of this particular molecule. Finally, we will touch upon the asymmetric Diels Alder reaction. The asymmetric Diels Alder reaction can be carried out in three different ways. It could be from chiral starting materials, where optically pure isomer of the diene or the dienophile is taken and it is reacted with the counterpart to give the corresponding asymmetric induction. Or a chiral auxiliary can be used. Chiral auxiliaries are temporarily attached to chiral pendant groups to the diene or the dienophile, which can be removed by cleavage or by hydrolysis kind of reaction, so that after the chiral induction takes place, the auxiliary can be removed and recycled. Last and the most popular methodology is to use a chiral Lewis acid. The chiral Lewis acid essentially is same principle as the Lewis acid catalysis, except that in the case of the chiral Lewis acid, the Lewis acid is initially coordinated to a chiral ligand, which makes the chiral Lewis acid, which in turn catalyzes the reaction of the Diels Alder reaction. Let us first of all try to understand the basic principle behind the asymmetric Diels Alder reaction. Now, if you consider the diene is a planar unit. The dienophile can either approach from the top face or from the bottom face, and these two faces are enantiotopic faces of the diene. If it approaches from the top face, it will produce one enantiomer. If it approaches from the bottom face, it will produce another enantiomer. In this example, what we have taken is a one substituted diene. The substituent is R group, for example, and one substituted dienophile where the substituent is X. Now, in addition to the approach from side A and side B, either from the top face or from the bottom face, the approach can be also endo or exo. So, there are four possible approaches: top face A approach with endo exo, and B side approach with an endo exo kind of an approach. So, all the four types of approaches are shown here, producing the corresponding stereoisomer in each case. Now, when the approach is taking place from either A side or B side, and if it is controlled as an endo approach, then you will produce a pair of enantiomers. So, these two isomers are enantiomers of each other. Similarly, if the approach from the A side or B side is taking place with an exclusive exo approach of the Diels Alder dienophile, you can see here the X group is exo, and here also the X group is exo, and that produces the corresponding diastereoisomer of this molecule. Now, these two structures, which are divided by this dashed line, which is the mirror plane, for example, these are mirror images of each other, so they are enantiomers. So, A and B are truly enantiotopic faces, produces an enantiomer. Similarly, these two molecules are also enantiomer, but if you take this molecule and compare it with this molecule here, in other words, the endo approached molecule and the exo approached molecule, they are diastereoisomeric in nature. Now, let us assume that the control is possible that we approach only from the A side and only through the endo side. Then this is the only molecule that would be produced or predominantly produced, which is the basic principle of the asymmetric synthesis, where you induce asymmetric chiral center chirality by asymmetric induction, for example, to produce a particular stereoisomer. So, by nature, the endo approach is the most preferred approach in a Diels Alder reaction, particularly when it is a Lewis acid catalyzed Diels Alder reaction. And if the Lewis acid also promotes the approach either from the A side or B side selectively, then you would have produced only single enantiomer or predominantly a single enantiomer of the adduct that is formed. This is illustrated for a simple 2 chiral center system. This can be extended to a 4 chiral center system also, as it is shown in this particular case, where you have 4 consecutive chiral centers that are produced by a Diels Alder reaction between a disubstituted diene and a disubstituted dienophile, as a generic example in this case. Here is an example where methyl mandalate is used as a chiral auxiliary, or you can call the starting material to be optically pure isomer because only one enantiomer of the methoxy mandelic acid derivative is formed with this particular enol ether, for example. Now, the Diels Alder reaction with this particular naphthoquinone derivative produces 97% diastereo selectively this particular adduct, where the pendant group and the hydrogen are trans with respect to each other. In other words, the approach is an endo approach, and the endo approach is essentially producing this particular molecule. This is essentially an anhydride of boric acid and acetic acid. The boron acetate you can call it. The correct terminology is that this is an anhydride of boric acid and acetic acid mixture. And this is essentially acting as a Lewis acid because boron is a Lewis acidic center that will coordinate to these 2 oxygen, chelate these 2 oxygens, and thereby catalyzing the reaction to produce this particular diastereoisomer. If this pendant group can be cleaved, then only one enantiomer of this molecule would be produced during the course of the Diels Alder reaction. Another example, a chiral sulfoxide is taken. Optically pure isomer of the chiral sulfoxide, of course, it is enantiopure diene, reacting with the dienophile, which is Melic anhydride. The initially formed Diels Alder adduct is essentially this particular case an exo kind of an adduct is what is formed during the course of the reaction. This is an allyl sulfoxide. Allyl sulfoxides undergo rearrangement by a 2,3 sigmatropic rearrangement to give the corresponding allyl sulfinate. The allyl sulfinate undergoes a lactonization with the anhydride, and that is responsible. That can undergo lactonization with either this carbonyl functional group or with this carbonyl functional group, for example, producing 2 types of lactone derivative, which is a bridged lactone derivative in this particular case. The reaction is not catalyzed by any Lewis acid. The reaction takes place either at room temperature for 40 days at yielding 65%, or it is carried out under high pressure of 13 kilobars pressure, yielding the product to be about 90% yield or so. Diels Alder reaction can also be promoted by high pressure because the orientation of the 2 diene and the dienophile would be favored under high pressure because you have a tight compact transition state that is being formed during the course of this reaction. Another example where the sulfoxide is actually attached to a dienophile. In the earlier case it was attached to a diene, now it is attached to a dienophile. Now let me first say something about the kinetic resolution. Kinetic resolution is a reaction where you take an racemic mixture of compound and only one enantiomer reacts preferentially, or one enantiomer reacts much faster than the other enantiomer, and thereby producing the cycloadduct or the reaction product from one enantiomer, leaving the other enantiomer intact. So you consider the mixture of enantiomers. This is a racemic mixture of the diene is what is taken. You can see this is a chiral center. So the racemic mixture of this diene reacts with the optically pure isomer of the sulfoxide. The reaction proceeds with only one of the enantiomers of the diene. With this particular configuration, the enantiomer is used for the Diels Alder reaction. It results in the 97% yield of this particular Diels Alder adduct. The trimethyl sulfoxide group is eliminated after the Diels Alder reaction is over, leaving the other diene, which is this particular configuration diene, which is an unreactive diene under this case, in about 50% enantiomeric excess and 40% yield. In other words, if you take 1:1 mixture of the enantiomers of the racemic mixture of this particular diene, only one of the diene is reacting with this configuration in the chiral center. The other diene with this configuration in the chiral center is unreactive under these conditions, and that is the basic principle of the kinetic resolution, which is illustrated by this particular example. These are some examples of Diels Alder reaction, either catalyzed by a Lewis acid, just like the Lewis acid that is shown here. So let us consider these reactions carefully. This cyclopentadiene reacts with this acrylamide derivative in the presence of water, for example, water can catalyze Diels Alder reaction through hydrogen bonding interaction, resulting in the formation of the two isomers of the diastereoisomers of the product that is being formed in this particular case. And the reaction, when it is catalyzed by a diethyl aluminum chloride, which is a Lewis acid, the aluminum can coordinate to or chelate to this particular derivative. This is a chiral derivative. So when aluminum coordinates to this, it catalyzes the reaction because the Lewis acid catalysis, which enhances the electrophilicity of the dienophile, for example. Under these conditions, the exo-endo ratio of the isomer is 20:1. Almost exclusively the endo isomer is formed during the course of the reaction. This is a chiral auxiliary that is coordinated to the aluminum center, for example. So this is an asymmetric catalysis of the Diels Alder reaction is what we are referring to in this particular case. This is a ligand which is a chiral ligand. It can coordinate to the iron, which in turn can coordinate to the chelate to the two carbonyl oxygens in this particular molecule. And it's a Lewis acid catalyzed asymmetric Diels Alder reaction where the Lewis acidic nature of the iron and the chiral nature of this particular ligand makes the entire Lewis acid as a chiral Lewis acid, and catalysis by chiral Lewis acid gives exclusively one enantiomer. In this particular case, in R isomer is formed in about 90% yield. Here is another example of a Diels Alder reaction where this chiral aluminum reagent is used as a catalyst, for example. So 10 mole% of this catalyst is used. The aluminum will essentially coordinate to these two carbonyl oxygens, catalyzing this reaction. Reaction takes place essentially at -78 degrees to give exclusively the endoadduct, which is shown here. The endoadduct is oxidized by means of an oxidizing agent to produce this ketone. In other words, this carbon-carbon bond is oxidized to the corresponding ketone. The ketone undergoes a Baeyer-Villiger kind of an oxidation to form a lactone, and the lactone undergoes further iodolactonization to give this particular product. The relative stereochemistry of the iodolactonization you can see is anti, as one would expect the iodine to be forming an iodonium ion, followed by attack of the oxygen of the lactone from the endo side, leaving the iodine in the exo side, for example, resulting in the formation of the trans isomer. The iodine and the OBN group in the benzyl oxy group, for example, they would be cis with respect to each other because iodine will be exo and this is also the same side. So those two are, relatively speaking, they are cis with respect to each other. And finally, the hydroxy functional group that is produced by the lactonization reaction becomes anti with respect to the hydroxy function iodine, which is adjacent position, for example. So the entire stereochemistry can be explained on the basis of the lactone that is being formed by the Diels Alder reaction, cleavage of the lactone followed by the attack of the lactone by iodolactonization to form the iodolactone that is shown in this particular stereochemistry of the product that is shown here. Here is an example where the derivative of tartaric acid, which is known as tadol, is used to complex the titanium dichloride. This is produced from reaction of the diol with the titanium tetrachloride or titanium dichloride diisopropoxide as the starting material. That is used as a catalyst. 0.1 equivalent, in other words 10 mole% is what is used as a catalyst, and that essentially affects the exo-endo ratio, as well as one enantiomer of the product is formed during the course of the catalysis of this chiral Lewis acid for this Diels Alder reaction. Another example where binol is used. Binol is 1,1-binaphthol is binol, and the R isomer of binol is a chelating agent that can chelate the titanium to the titanium dichloride derivative. The two isopropoxide groups can be substituted by a binol derivative. The Diels Alder reaction essentially initially produces the diketone, which is reduced by lithium aluminum hydride to the corresponding diol. You can see very high enantiomeric excess of this particular isomer can be formed. You have essentially generated 5 stereocenters in one shot in this particular reaction by means of a Diels Alder reaction followed by reduction of the carbonyl to the corresponding hydroxy functional group. These are again some more examples of the Diels Alder reaction produced by catalysis using this copper bisoxazolene derivative as the Lewis acid catalyst. In Lewis acid catalyst essentially coordinates or chelates to these two oxygens of the dienophile. In this case, the cyclohexadiene or 1-phenyl substituted butadiene or this particular enol acetate diene is what is used as a diene component, resulting in the formation of very high endoselectivity with a high enantiomeric excess of the product that is formed during the course of the Diels Alder reaction in this case. So let us conclude this particular module. What we have seen in this module is the intramolecular versions of Diels Alder reaction to produce fused and bridged bicyclic systems. If it is a one substituted derivative, then it will be a fused bicyclic system. If it is a two substituted diene derivative, then it will be a bridged bicyclic system. I also seen Diels Alder reactions of heteroatom substituted dienes and dienophile. Predominantly oxygen and nitrogen heteroatoms are what is illustrated in the examples. Catalysis by Diels Alder reaction by Lewis acid catalyst, as some examples have been seen, where the Lewis acid coordinates to the lone pair of electron in the dienophile, reducing the homo-LUMO energy levels of the dienophile, bringing the homo-LUMO energy gap of the diene-dienophile combination closer together and thereby reducing the activation barrier. Finally, the basic principle behind the asymmetric Diels Alder reaction and some examples of enantioselective asymmetric Diels Alder reaction, particularly those catalyzed by chiral Lewis acid, have been illustrated in this particular module. I hope you enjoyed the module. Thank you very much for your kind attention. Thank you.